Okay, next. So we next have Nick Chancellor, who's going to tell us about quantum annealing from theory to practice.
Yep.
So go for it.
So you might guess from my fairly generic title that I'm actually going to talk about a mixture of things. Also, if you've read my abstract, you would definitely realize that at least if I'm being faithful to the abstract, which I will be, I'm going to be talking about a whole mixture of different work that we've done. Mostly at Durham, a little bit at a company that I work in part-time, which that will be made there, but a slight backgrounds. So what this talk is about, and acknowledgement of collaborators. First, a bit of talk that many of you have probably already seen, sort of why we need some theory that goes beyond the adiabatic limit and how you can start making some progress to that. It's good to see this actually in many ways is representing a direction the field is taking. So maybe at some point I won't need to put these slides in the talk anymore because it'll just be given. Next I'll be talking a bit about work on encoding, previewing a little bit Paya's talk, but I won't steal his thunder. I'll just mention it and give a little bit of context. And then finally talk about the importance of finding good use cases and some work in that direction. This includes work with our fluid mechanics expert, Omer Rathor, who might be able to help if you have specific questions on how the problem is set up. Fortunately, he's in the audience, so instead of me just saying I don't know, I can defer to him. That's all very preliminary work anyway, so they're not going to be too much substantial to talk about there, but it's good to show what we're doing. So first, if we think about a very sort of theoretical, traditional picture that people have looked at quite a while ago that was sort of early motivation for at least quantum annealing optimization, this traditional picture of adiabatic quantum computing, you map a hard optimization problem, slowly change the driver, Hamiltonian, from an easily prepared ground state and to a more difficult to prepare ground state, and the adiabatic theorem of quantum mechanics keeps you in the ground state if you go slowly enough. So, the advantage of this picture, why is this a picture that people use a lot? Well, first off, you have an algorithm that's effectively deterministic. That's nice. And you have an intuitive picture involving only two energy levels. This is nice theoretically. You can do all kinds of fun theory with this. But if we assume what most computer scientists assume, that P is not equal to NP, in other words, that hard optimization problems exist, then the total runtime needs to be exponential in the size of the problem, and you need to remain coherent for a long time, which, as our colleagues at D-Wave can tell us, is very difficult to do. So this actually probably isn't what you really want to do. There are extensions of the adiabatic theorem. I'm going to just highlight this paper by Callison and Lidar that mentioned some of those. That is good work. That's just not what I'm going to be talking about today. So what can be done? So one thing you can do is you can somehow restore coherence and do, for instance, error correction. There is some really nice work done in this direction, but it's not what this talk is about. And I put a ridge there because this is hard work. And you have to mitigate not all the errors, but enough errors for a very long time. From our group, Gemma Bennett will have a talk that does some work in this direction. The other option is to instead do a lot of really short runs. And this is kind of what you have to do experimentally in practice anyway, because you just don't have that much coherence time. So you need exponentially many runs to succeed, to get the right answer. You're sort of, unless you're breaking something in complexity theory, something that most people believe is true, you're going to have an exponentially low success probability in this case. Otherwise, you're solving a NP hard optimization problem in polynomial time, which is not proven but believed to not be possible. And so this is kind of conceptually unsatisfying. It feels like you're playing the lottery. Some people, I've heard talks where people say, oh yeah, you have an exponentially decreasing success probability, so ignore that. But actually, we always expect these algorithms to be exponentially hard. So you actually shouldn't ignore that case. And I think psychologically, this feels really bad. This feels like you're working hard and earning your money, this feels like you're playing the lottery and just hoping to do well. But I think actually there's much more of a case for this kind of situation than this one. So, moving on, what can we say in this case? So we have this nice adiabatic theorem, and I don't expect you to sort of grok everything from this slide, but there's a nice paper that gives all this. But basically, in the limit of fast anneals, we have the adiabatic theorem, or slow anneals. We can extend this to faster anneals to some extent, but you have to make assumptions about the structure. I'm not going to go through the details of that, because again, that's not what this talk is about. But what can you say in general if you have a rapid quench? And one thing you can say is you can actually make an argument based on energy conservation. And you can basically trotterize this into stair steps and say, well, you have two parts of the stair step. You have the part where you go across, which is a closed system time evolution. So a closed system time evolution, you have energy conservation. Overall, your energy is conserved. If you start your driver in its ground state, you have to be transferring energy. You have to be entering into a higher excited state, or partially higher excited state in the driver if there's any non-trivial dynamics, which means your energy with respect to the problem necessarily has to decrease. Then you have stages where you turn your driver Hamiltonian down. That will actually reduce this energy that's been stored in your driver Hamiltonian. So further actually pulls energy out of the system. And the result is that your expectation with respect to your problem Hamiltonian, after any sort of monotonic quench, will always be lower than it was to start with, than it was with your initial distribution. And this is a somewhat weak result, but it's very general. All you have to have is a monotonic quench, meaning this gamma, this ratio of A over B. Remember, A is the strength of the driver, B is the strength of the problem. Has to decrease over time. You have to start in the ground state of your driver Hamiltonian. And there's a technical condition that your driver can't be gapless, which isn't really a concern for real problems. But there are some sort of infinite size systems where that would probably mess things up. We just didn't consider that case, so we said we can't show anything there. What is allowed? Well, unlike anything related to adiabatic theorem, there's no limit on how fast your algorithms run if you're considering this. Discontinuities in this gamma parameter are perfectly well allowed, so even parts where you're running infinitely fast, that's fine for this. We've made no reference to how fast this parameter is changing. And importantly, this driver Hamiltonian does not have to be diagonal in an orthogonal basis to the problem Hamiltonian, which means we could have a biased starting state. So if we're starting with a transverse field driver, what this means is we do better than random guessing. That's not so impressive. But if you already biased yourself, have a driver that's actually biased towards good states initially, where its ground state includes some z terms, then actually you can start from a very good state and you're guaranteed to hopefully get at least a little bit better, at least not get any worse. So you can't do something like this, like a reverse anneal, because this wouldn't be monotonic. But in general, you can do all kinds of wacky things where it flattens and then goes and stuff like that. So an intuitive example, something where you can't apply the adiabatic theorem, two-stage quantum walk. So this is your gamma, so this ratio between A and B. You start at one parameter, evolve for some time, change it, evolve some more. As we can see, our energy expectation, initially our total energy expectation is 0, because we start off in the, we have energy conservation and we start off in the plus state, because this is unbiased. And then when we turn this gamma down, that overall expectation goes down, and then we have the two components, the problem and the driver, and they cancel each other out. As you can see, when you have a wiggle here, you have an opposite wiggle down here. The success probability, which the theory we've done doesn't say anything about, but in this case it does go up, although there's not a theoretical guarantee of that. And a non-instantaneous quench is effectively, you can think of it as an infinite stage quantum walk. This is actually how we did our proof. So, why is this important? Well, it's general, but it is a bit weak, because it's just saying your doing at least as good as your initial state. And if you have some non-trivial dynamics, you'll do better. But what this means is that if you're thinking of designing protocols, this actually is important because you don't have to worry about your dynamics being counterproductive. You just say, look, I want to maximize the amount of my dynamics. I know that these dynamics are going to push me toward lower energy states. So if I just maximize how much stuff is happening, that should be a good way to design protocol. You can bias, I'll discuss on this later. And it's, again, you can understand dynamics very far from the adiabatic limit. So a little bit on how you actually can do this, how you actually can try to understand what's going on here, is you can model the dynamics in a two-state subspace. And basically what you can say is you can say, I'm going to look at not every two subspace of between two states, 2-bit strings, because there's exponentially many of them, so that would be a very large number, so you couldn't do that in a large system, but I'm just going to sample from, let's say, single bit flips if I'm doing a driver, on X direction driver, and then say, okay, what's the average? We've defined a quantity that measures the amount of dynamics, and say, if we have a different gamma value, on average, what level of dynamics do we have? As we see here, this is made of two quantities, one that measures how much you can see the problem, and one that measures, so that one, when gamma is 0, you have, you can't really see your problem at all. Then you have this one, which measures how much you're actually allowed to flip. And when you take the product of the two, you have a peak. And so you see one increases, one decreases the product of the two. You have a peak here. The reason you don't just, this doesn't just say, oh, have a maximum amount of sigma x terms, is that you're starting in an eigenstate. So that won't give you any dynamics because it's an eigenstate, nothing happens. So what if you actually try to optimize the protocol in this way, optimize an annealing schedule? You can do a bit better than a linear schedule. The important thing here is this is a quantity that even for a large system, you could calculate efficiently. So unlike these considerations where you say, I'm going to use a spectral gap to optimize my annealing schedule, oh, but I don't actually know my spectral gap and finding it's probably harder than actually solving the problem. This is, well, we do some sampling within two-level systems. We can just do that classically to estimate the amount of dynamics. And what I'm doing is I'm saying, I'm going to have faith that the dynamics is doing the right thing. I have theory that argues that. And then I'm just going to maximize the amount of dynamics. So I'm going to slow down when there's the most effect of my driver and speed up when not much is going on. And you can do that. And just for this example instance of a random spin glass, you can do a bit better. There honestly probably needs to be more work studying this, but we gave sort of a proof of principle that these ideas can be useful.
What is chi?
What is chi? So the way I've defined it, so chi is this quantity here, which is measures the amount of dynamics. So this T is measuring the amount of transfer you have between the classical states. It's the amount of bit flipping. This D measures how much you're actually able to see the problem. You take a product of the two, and you get a quantity that necessarily will peak, because you have a product of two things that tend to 0 on either side. So if it's non-trivial anywhere, you'll get at least one. Well, yeah, you'll get at least one peak. And so yeah, this is for just a single Sherrington-Kirkpatrick instance. Again, more work should probably be done to investigate this, but just proof of principle that these ideas can be useful. So, as I've actually now highlighted twice, and this is going to be the next bit of the talk that I mentioned, hybrid protocols are possible using this mechanism, but you have to be careful what you're using. So there are several known techniques to basically bias toward a good state, and not all of them are compatible with this energy conservation argument or energy redistribution argument In particular, anything with open systems is right out because we're using closed system arguments. So the traditional sort of reverse annealing relies on dissipation, not suitable. The more coherent version of reverse annealing, the ones we found, again, it's not compatible because your schedule isn't monotonic or you're involving 3 Hamiltonians. Maybe you could argue versions of that you could have some extension of this, but so far that's not been done. But what you can do is do something I hinted at before, where you use a driver that's biased. So a driver that contains not only the x terms, but z terms. And this is compatible with the arguments we've made. So this is just a reference to our paper again. It is compatible with those arguments because remember that the driver does not have to be diagonal on an orthogonal basis to the problem Hamiltonian. And so all of these arguments that you must be improving your energy, or at least not doing any worse, do apply in that case. So this nicely segues into the next part of the talk, which is the importance of hybrid algorithms. And I'll talk a bit about what I mean by hybrid algorithms, but annealers are very powerful in some ways, but very limited in others. And I just pointed out here, this is actually true for all the paradigms of quantum computing, but this is a quantum annealing conference, so I'm going to single out annealers. But they'll be very limited in others. And gate model quantum computers also will be, boson samplers also will be, anything else you can imagine also will be. For them to be genuinely useful, we must take advantage of the computational power and circumvent limitations. And so this naturally indicates an argument where you're having a coprocessor, where you're having a QPU that you're calling at some points to do parts of your calculation that are hard to do classically, but you're not just trying to do everything on a very limited processor. This is actually, if you think about the way we do a lot of classical computing, this is actually very natural. This, in many ways, quantum computing is new and exciting, but I would argue this is actually a way in which it isn't necessarily, right? We have graphics cards that take a specific kind of use case of workload off of your computer, either doing graphics or now doing parallel simulation, off of your CPU, but you still have a CPU because CPUs are good at the general purpose task, and then you have specific tasks. In the cases I'm talking about here, the specific task would be sampling from a hard optimization problem, or maybe doing a single update on a hard optimization problem, then handing back off to a classical algorithm to do some things that are easy to do classically and going back and forth. There's no reason to think that the same logic won't apply in quantum, and one key thing that this motivates is having, eventually, fast interconnects and co-location between HPC infrastructure and whatever quantum architectures you have. So the Jülich Supercomputing Center in Europe, for instance, is looking at this goal. There's a perspective paper I've written with Adam Callison, who might be attending later in the conference, that I just like to highlight here, that really goes through a lot of this. So let's talk about some of the things you can actually do to look at hybrid protocols. So reverse annealing and many related protocols. I talked about these a few slides ago, but let's go back. And this is, I'm not going to fully go through this work here. I have in previous talks, but this is basically that you can show, you can use, this is just an example of what you can do. Remember when we talked about how you use this as a subroutine to do some updates? What that necessarily means is you should be able to bias in a guess. So there are many ways to bias, as in a few slides ago, and this opens up sort of new families of algorithms. So I used to have a slide with papers that use reverse annealing. Then there got to be way too many to fit on a slide, so now I don't have a slide anymore for that because I couldn't come up with a fair way to decide which ones go on the slide. There are, just highlighting other ways you can be hybrid. There are protocols typically will also allow local bias adjustments. So this is just another example of some work where you can use reverse annealing to bias towards a solution candidate, then use the anneal offset features, this is on a D-wave, use an anneal offset feature to, on problems that have some planted solutions, so you know what the solution is, but you want more flexible solutions. So you bias this towards ones where some of the spins can fluctuate more freely, and you can actually find more flexible solutions at the cost of some optimality. And it's useful if some parts of your objective are actually too expensive to encode, and there's examples of this given in this paper here. This is just sort of a lightning summary of some of the things you can do for hybrid. I encourage you to read the paper if you want more details on this. But this is, if you were thinking of a reverse anneal, this S is your annealing parameter, so it's very similar to this gamma we had before. Lower S is more fluctuations, so you have some of your qubits you have more or less fluctuation on. So you can abstractly represent these locally biased searches. And again, I'm not going to go through the full idea here, but basically the idea is to abstractly represent calls to the processor here in this figure B, where you say, you know what, I have a processor, I have a state I'm biasing toward, and I have what my problem is, and then in between there I have stages of classical computation, which this only takes one input, this can take multiple inputs to then calculate what you're having. So this naturally suggests things like genetic-like algorithms, which is what this focus on this paper I'm talking about here focuses. So now those were kind of all just very quickly one slide on different fun things you can do with hybrid. Now let's go into more detail on specific other things you can do. So what we're going to talk about here is now how you encode your problem. So we've talked about the algorithms that you can use to solve your problem. Now let's think about how you encode your problem. And you might think, well, okay, this is all known stuff, right? We all know about how to turn any given problem into a QUBO. There's all this nice story about how all NP-complete problems can be mapped to each other with polynomial overheads. But we're talking about near-term limited devices. We really want to squeeze efficiency out of this. There was some discussion of this in the previous talk. Under a different context, under the context of optimization, we of course also want to do this. So the specific case I'm going to talk about here is higher than binary discrete problems. So things like a truck can go down any of 3 roads, a task can be scheduled at any of 5 times, a component can be placed in 7th place on a chip, and we can mathematically define this just with sort of X terms that say, okay, these terms are 0 unless one variable takes a particular value. This, of course, doesn't describe what most hardware looks like. Most hardware is qubits, so how do we map this to qubits? Well, there's 3 ways to do this. One way is to map each of these configurations to a bit string. And this is what I'm going to call binary encoding. This is the most efficient you can do in terms of number of bits. However, the problem is if you're thinking of making interactions between these, general interactions, some interactions you can do efficiently, but general interactions, you need very high order terms. And those are hard to make in quantum annealers. So this is, if you have a problem that's conducive to the structure, like say a factoring problem, this is absolutely what you want to do. You don't want to even consider these other 2. However, if you have a problem that doesn't, like any of the 3 examples I gave on the last slide, you either can do one-hot, where you say, this is the traditional way, where you take, okay, each variable taking a value corresponds to a qubit. I have a constraint that only one of these can be 1 and all the others have to be 0. And then interactions between those qubits represent my interactions between variables. There's a new thing that we came up with, which is a domain wall encoding, where what you encode this in instead is a position in a domain wall on a chain. And so you look at an Ising spin chain with 2 fictional fixed spins at the end that I make to field terms. So I actually get 1 fewer binary variable and get much less connectivity And when you go to minor embed, it turns out this less connectivity makes a difference. We've seen this experimentally, and basically you just map encoded values to these qubit configurations that correspond to different domain wall positions, and you frustrated this chain so that there's no way you can have 0 domain walls. You always have to either frustrate the connection with one of the 2 fictional spins on the end, or you have to frustrate a connection intermediately, and unless you've included some interaction terms, those will all be degenerate. Once you do, the degeneracy is broken, but you still have a low energy subspace that looks like this. So this gives you improved performance for maximum 3 coloring problems. So when we looked at this, we even found that if we took this K coloring problem and we used an domain wall on a 2000Q, so on the older D-Wave processor, and 1 hot on the newer one, using a more clever encoding on the older processor actually did better than using a newer processor with a less efficient encoding. Now, it looks like where a lot of this advantage comes from is the fact that this embeds more efficiently. There's still a lot of work to be done, but when people have tried this on fully connected architectures, it seems like a lot of this advantage largely disappears, but we have a lot of architectures that are not fully connected, so that suggests that this is still worth doing. We've also looked a little bit on the effective dynamics. You notice my slide background has changed because of who I worked with on this. And here we've looked at what happens if you have a 1-hot encoding. You only can act perturbatively. Basically, if you want to move through your subspace, if you're doing single bit flips, you have to go through an invalid space, invalid configuration, whereas domain wall encoding you don't. Of course, these will also be minor embedded if you're doing it on a D-Wave, but that still means you have to flip 2 minor embedding chains rather than 1 in this case, or at least 2. So it still looks like it gives you an advantage. And what we've done is we've sort of assumed a frozen-in thermal distribution. This is using actually an easy problem. We didn't want to look at a computationally hard problem. We wanted to look at something we could simulate easily with classical Monte Carlo, but we wanted to look at really what the effect is on the embedding. And then we've done some work on verifying that quantum fluctuations can indeed be safely ignored. I'm not going to give that in this talk. But what we find is, indeed, if we look at the effective temperature over the maximum coupling, what we find is that a domain wall encoding effectively gives you a lower temperature. You notice we've extended the size of this problem 1 further for the domain wall encoding. That's because it failed to embed here. So this also allows you to actually embed bigger problems. Or, sorry, it didn't fail to embed, it failed to find any solutions at all here. And if we correspond that, if we then take this annealing schedule and back calculate the ratio of A and B, where the point where it froze, which corresponds to the ratio of A and B, again, we find that this is freezing later in the evolution. This kind of makes sense. You're having to flip fewer of these spins. So this could be used in conjunction with some of the very nice work we've seen before about facilitating chain flips in minor embedded systems. And yeah, this has been accepted in philosophical transactions A, but it's in the awkward stage of accepted, but I don't have a reference yet to give, so I'll reference the archive. So you can try this yourself. Just want to flash this up really quickly because I think sometimes, you know, a big barrier to something like this is you hear of a cool idea, but it's just time. You don't have the time to encode it, so we've actually written some code to do this, to implement this encoding, that you can actually just download. It's associated with the paper on the Durham, basically, data repository. It also has the data repository for the paper, but probably the more interesting thing if you want to do something with the actual code. I don't think I have time to go through exactly how it works, but you can do a simple 3 coloring problem. This will be a 9 variable problem, 9 qubit problem, and so your H and J's end up like this. Your problem implementation, because this is a coloring problem, so these are the constraints that make it so you can't color adjacent things on the chain the same color. And you can, this kappa is basically a Lagrange parameter to determine how strongly you enforce this chain, and so you can implement an overall Hamiltonian. If you did a one-hot encoding of this, you'd have to use 3 more qubits, so 12. So there's also some new work on encoding. I'm not going to talk about this. This is the work Pi has done, so I encourage you to listen to that talk. It's interesting preliminary work, basically looking at can we approximate k-hot constraints, so where we now want k1s using only linear terms. And this was actually done with a consumer data science company to examine realistic problems, which actually nicely segues into the next part of the talk, because I realize I have not that much time before questions, which is how do we actually find use cases for this quantum annealing? So far I've talked a bit about the theory, a bit about how we want to sort of probably move the theory, and there's a lot of work already being done in this direction, but motivating further how we want to sort of move the theory away from the traditional adiabatic picture. Talked a bit about the importance of being hybrid and having good encodings, and now want to talk a little bit about actually finding good use cases. And there's some, not the subject of this talk, but there is some discussion on how to think about this systematically that I've done a while ago now. And so this is going to be about a very preliminary project with a new postdoc we've gotten through the Quantum Enhanced and Verified Exascale Computing project. And there's actually another relevant project I just want to point out, which is the CCPQC, which is a collaborative computational project. This actually isn't directly involved with that, but their two are closely related. You should contact Viv Kendon, who unfortunately for a scheduling conflict has just left the room, but you can speak with, if you want to know more about these projects, you can talk to her. But this is about talking about one part of the Quebec project, very preliminary work, so I'm not going to have final results. You're not meant to find these results very compelling because they're not done yet. But the basic idea is, let's look at a realistic case, load balancing for fluids problems. So, what we're imagining here is we're imagining a case where you have a fluids dynamic problem, so this is a velocity field, and what you're doing is you design a dynamic grid, adaptive grid, so that's not what we do, we just assume you can do that classically. But then when you have this adaptive grid, a non-trivial question becomes, how do I allocate this fairly to different processors? So here's an example of a problem called sod shock, and then what we look at is how we allocate these adaptive grid points to different processors in a way that's, it's basically what's called a number partitioning problem, in a way that we, as fairly as possible, divide the nodes, the load between these points. This can be adapted to more complicated problems. So here we have sort of hypersonic flow with obstacles. Again, similar idea, adaptive grid based on where there are gradients in this velocity field. You see we don't do much out here because nothing's changing. We do a whole lot here, and we do a moderate amount there. And then this is just, again, a classical solution of how you do it. One more, even more complicated example would be flames in 3D. So this is now not velocity, not fluid velocity, but fuel concentration. And you can see you can similarly have 3D boxes. You can't easily visualize how we're splitting up between the processors because it's 3D. So what we'll do is we'll take a slice, and this is just looking at a slice, and you again see a similar picture. This problem would probably be too large to fit on a current quantum annealer, at least without doing something clever. But you can see in principle, this is a way to get an interesting hard optimization problem that can indirectly speed up something people do in computer science. You're not directly solving any of the fluids equations. What you're actually doing is using the classical resources more efficiently. A really good example of sort of a hybrid application. Again, here's a very preliminary result that literally was just a couple days ago, looking at the simplest example I gave on the first slide. We do iterative partitioning in 4 stages, but I've only shown the last one, and looked at sort of quantum annealing simulated annealing and greedy method, and it's kind of hard. The idea is to get as even a possible split, but you can't generally do that. You can't do that perfectly, even if you have the ideal optimizer. You can see if you squint, probably the annealing's doing a bit better than the greedy algorithm. It's hard to tell because some points are on top of each other, and probably about the same as simulated annealing. But obviously, this is where the work in progress disclaimer comes in. You shouldn't take this and go, oh wow, that's like a great result that shows that I should use a quantum annealer for this, but more, this is a preliminary result that shows that we're working on this and shows sort of a direction to go into looking at how to actually use these on realistic problems and how you can really take the full use case and sort of break it down into what the problems are. And of course, more results will be forthcoming on this in the future. With that, I believe I'm done, and it's right about time for questions if I have the timing understood correctly.
Okay, so as Nick pointed out, Durham apologises, but she has a schedule clash, so had to depart a little bit earlier. And I'm going to take over the chairing for the questions. Glenn.
Okay, thank you for the talk. I have a question regarding the rapid quench.
Oh yeah, of course.
Rapid quenches. Yeah. So, do I understand correctly, meaning that if I have some solution, I can use the rapid quench to always improve and get something better? Is this correct? Because I saw that there were some limitations on the protocol I can apply, but because
Yeah, so the idea is if you have if you have
an
a
approximate-
state, it has to be the ground state of a driver.
Yeah.
So yeah. So now, there's no guarantee on how much it will improve, right?
Mhm.
So if you have already, well, obviously, if you're, and so this is the energy expectation with respect to the problem Hamiltonian. So the most trivial example would be an example where you actually can improve at all, is I start in the ground state and my driver is my problem statement, in which case you obviously don't improve at all, but that's a case where you have no dynamics. What you could have though is if you have a state that you're starting in, or that you think is a good solution candidate, you can then take that, rotate the, say, okay, I'm going to define my driver as spin vectors, mostly in the z direction, where that's the ground state. So I just, if it's a 0, I have if it's a spin up, I have the field pointing in the appropriate direction down. But then I tilt that a little bit, so that will make my energy expectation with my problem a little higher. And with respect to that, I'll always have a lower energy expectation with respect to my problem Hamiltonian. So I'll always be drawing a solution that has a lower energy expectation. Or if there's any non-trivial dynamics, it'll be lower. If there's no dynamics, it'll be exactly the same. It can't be higher, is the point. You can't, as long as you follow these conditions, because one of the stages has energy conservation, and the other, you're pulling energy out of the system effectively in a picture where you've reparameterized it, you can never actually end up at a higher energy. So there is sort of a no free lunch here. There's not a guarantee on how much you improve. So you can't just say, well, okay, this will definitely always, by the adiabatic theorem, if you wait long enough, it will always give you the most optimal solution. But beyond that, there's not really a guarantee that, there's not a free lunch, let's put it that way. There's no way, in pathological cases, the improvement will be very small. But yeah, that's the idea. And intuitively, the way you do this is you consider this as the limit of a sort of stair step, where you have one stage that looks like a continuous time quantum walk, so it's energy conserving, and then another stage where you have no dynamics, but you turn down this ratio. And you can argue that neither of those stages can, increase the expectation of your problem Hamiltonian beyond where you started. And that's basically the theoretical argument that comes in here.
So just to specify, this doesn't mean that I can get out of local minima and still be stuck in a local minima because it's not getting worse.
You could, yeah.
I could
Yeah.
just get stuck there.
You could be stuck. I mean, in general, if you have a non-trivial driver, the adiabatic theorem will still apply in these cases. So you could have an argument that you'd eventually get unstuck. But the time to do that may be the lifetime of the universe, so it may be, theoretically interesting, but irrelevant from a practical perspective.
Okay, thank you.
So for the domain wall encoding, do you actually, is it like you do the encoding of the problem and then still send it to find a minor embedding to the D-wave heuristics, or do you also, is there also a way of that you use the encoding taking into account like topological constraints of the chip that you know where you should put it on the chip, like where's the cell of high connectivity or anything like that?
So in our study, we just used the standard minor embedding protocols on the D-Wave devices. You could do something more clever. So all we did basically everything in the most standard way we could think of, and just changing the problem statement. So at the highest level where you have your Cubo or Ising model, it's easier to think about as an Ising model that you can do it with the Cubo. Just change that statement and then feed it in like it's a black box. Now in some ways you could argue that this probably actually gives a slight advantage to one-hot encoding because that's probably more like the problems where these have been tested and developed on. So you might think there could be some gains by playing around with clever embedding strategies that are aware of these structures. The other thing that could be very interesting is if you have a specific kind of problem that you know has a specific structure when you use this encoding, you could actually build your hardware architecture to map, to match a type of problem. And there are many problems actually that have, relatively similar structure. And this, potentially could be something interesting in the future. Obviously, building hardware is difficult, so this isn't like, okay guys, do this, I want to see it in 6 months. Obviously, you can't do that. But in the long term, in the very far future, you could imagine something like that.
All right, thank you.
Yep.
Time for a couple more questions, if anybody has. Matthias.
Yeah, thank you very much.
No problem.
On the very last slide,
Yep.
how did you measure the percentage of work done by subtasks? Or
I believe we did, Omar, if you want to.
It's a bit tricky.
just so to the record.
My moment's in the spotlight.
Yep.
10 seconds of fame.
Okay, so you're right that sometimes for these adaptive mesh cases, it's a bit difficult to define what you consider work, especially for the flame cases, because the points within the flame experience much bigger work than the points outside. But for the simple case of the solid shock tube, total work on a box or patch of confinement was the number of cells contained in it. So the total work is basically all the cells, and the percentage of work in each processor is a subset of cells allocated to each individual partition.
So,
I'm not saying that's the best way for all cases, for reasons we can discuss as well, but I think it's a good approximation for these simple non-reactive cases.
Yeah.
Does that answer your question?
Oh, yeah.
so it's number partitioning. We are thinking about possibly generalizing to graph partitioning, or Omar is thinking about possibly generalizing to graph partitioning, but the emphasis here is preliminary work. Again, not that you should think, oh wow, this is the most best thing in quantum annealing to happen in the last 5 years. No, it's very preliminary.
I should also add for adaptive mesh refinement, there's a constraint because this is a box structure, so each box has a lot of interconnectivity between each other, right? So you don't want to actually split the box itself, like the patches. So you assign different boxes to different processors. Different boxes might also be different sizes as well. So
Any final questions for Nick? If not, let's thank Nick again. Thank you, Nick.